In this lecture, I'd like to give some advice for graduate students, particularly for graduate students in computer science. As disclaimer, these are my personal opinions. They may or may not be exaggerated. I recommend that you also ask other people and talk to them about graduate studies. As a matter of personal style, I prefer to start with strong statements and maybe refine a bit later, rather than being overly polite and correct and modifying all statements so much that they become almost meaningless. What research do I know most about? I try to actively publish, at the moment, in deep learning, computer graphics, and computer vision. There's some overlap with image processing, remote sensing, and visualization, and I have some exposure to AI, machine learning, data mining, robotics, GIS, and computational geometry. What are some main goals for people getting into graduate studies? First, getting a good job in academia. Second, getting a good job in industry. Or maybe solving important problems for society. Maybe personal enrichment, the quest for gaining knowledge, or the quest for wrestling with difficult problems. Others enjoy the relaxed student lifestyle. And even others just want to avoid getting a real job and like to hide out at the university for a few more years. My belief is that faculty in the CS program are mainly exciting about supporting the first 4 goals. The other 2 we are in general less excited about. Graduate studies are a really wonderful opportunity, and learning is a really great thing to do, and it's a real privilege to be able to be involved in learning more and in working in research. I therefore think that graduate studies should be approached seriously. Maybe more specifically, for my research group, I set the main goal is to conduct and publish high-quality research. And my goal for my graduate students, and also postdocs, is they conduct and publish high-quality research together with me, and that they should get a very good job after they leave my research group. This may be different for many other professors, but to me it is really important that students and postdocs leaving the university can get a good job afterwards. That then also influences what type of research problems I am working on personally. Because I believe that students should learn skills that are coveted afterwards, and that means often that the students should learn practical skills that are coveted in industry as well as academia. Here are some questions you might ask yourself before committing to graduate studies. What is the difference between a PhD graduate and an undergraduate with 5 years working experience? Loosely saying that an MS plus PhD degree would take about 5 years. Can a person with a PhD MS really get a better job than an undergraduate with working experience? I think that a graduate student should have some more advanced skills, maybe be able to solve more difficult or more complex problems, or being able to determine if a problem is important or solvable. In addition, a PhD student should also be able to pose interesting research problems. And in this context, evaluate if a problem is a useful or potential research problem. However, not all graduate students learn advanced skills. Sometimes an undergraduate student with work experience learns more advanced skills and can get a better job. I believe that we as a university can help many students get better jobs, but they do have to participate and also work for it. In particular, in computer science, there are many really exciting academic jobs and also research jobs available in industry at the moment. I really think that an advanced degree with the opportunity to work in some of these really interesting jobs is a worthwhile investment. Now let's discuss the following problem. What skills are important for high-quality research? I will discuss the love of research, system skills, mathematics, subject knowledge, English, and creativity. First, the love of research. You have to love research and really be passionate about it. You yourself have to be intrinsically motivated to do it, not because someone tells you to, but because you personally really like to do it. One of my professors told me that doing research is like training for the Olympics. It takes long hours and you compete with the other people around the world that are excellent and also invest a lot of time. If you treat research as a 40-hour job that prevents you from enjoying your other hobbies in the evenings or on weekends, I believe there's little chance of success. At least, I have not observed someone being successful in research with only working 40 hours. I think most good people invest at least 60 hours of time per week if they want to do a successful PhD degree. Now, close to deadlines, it is almost always more. This is not pure working time in the sense of maybe programming or deriving equations. This also includes reading books and papers, maybe even in other areas, thinking about research, discussing research, watching online lectures, or in a group discussing maybe recent papers, all sorts of activities. So people can be more or less extreme about that. It's hard to say a very particular amount of time you should be investing. You really have to find out what works for you. But from my experience, what is really important is that a student and an advisor are really excited about the research topic and really want to work on it together and collaboratively. It really doesn't work well if a PhD student in particular thinks about himself or herself as an employee and wants to get detailed instructions from an advisor without being personally invested in a research topic. Under system skills, I'm grouping various skills that could be called getting things to work in practice skills. For example, programming skills. Right now, for example, I would use Python and PyTorch mainly. Others might use C++, MATLAB, CUDA, but there's a very large range of tools that people use in computer science. You should have the ability to manage and write larger projects. Maybe 5,000 to 25,000 lines of code are not uncommon in computer science. Also, nowadays, very often, you have to integrate lots of code from the internet and from other people and build systems by combining existing code. In some areas of computer science, the amount of code written can be a lot less. These are typically the more theoretical areas, and there some of the papers, they can be written with 2 lines of code or 3 lines of code, and some explanations why these 3 lines of code are actually useful. Further, we have low-level algorithm development, debugging, knowledge of computer architecture to optimize code, maybe knowledge of GPU architecture, and related things. Maybe something also like algorithms and data structures to help you develop efficient solutions. Third, mathematics skills. There are many different areas of mathematics, and I'm just listing a few on this slide. So naturally, one can ask what mathematics is most important. Of course, what mathematics is most important depends on the research direction. For my current research, I can give the following advice, while at the same time, of course, you have to consider these changes from research direction to research direction. However, I think overall in computer science, this type of research is probably the most dominant, so these types of mathematics would be the most dominant overall. So you do need a solid basis in linear algebra and calculus, and also in multivariate calculus. Nowadays, regrettably, many computer science curricula took out a lot of the mathematics, and you might not have even heard of multivariate calculus during your undergraduate studies. Probability and statistics is also very important. In my experience, these topics are the foundation, and you have to add more to your knowledge than what you learned during undergraduate. You took a linear algebra course, sure, but during graduate studies, you might read some more advanced linear algebra books. You might look at some more graduate level material related to linear algebra. Multivariate calculus, also maybe you took an undergrad course, but you might want to add to your knowledge in that area, same as probability and statistics. Maybe it's revising undergrad material is one step, but also look for graduate courses, look for additional opportunities to improve your knowledge in these areas. Optimization is typically not studied in undergraduate computer science. This is definitely an area to get into. Again, taking one course in optimization is not nearly enough for doing research in optimization. You might have to consider taking 1, 2, 3, 4, 5 courses, read multiple books in that area. Machine learning, it's not really mathematics, but it's more like computational statistics and optimization. However, a lot of the mathematics, so to say, used in machine learning is very specific to the field, and it kind of has to be studied in the context of machine learning. You might not hear this type of mathematics by just taking a statistics course. Some of the machine learning uses functional analysis, but maybe not the first thing to start. Very interesting other topics, again, maybe not strictly mathematics, but more like mathematics-like background, information theory and estimation theory are some great courses to take. Also, of course, in the beginning of your studies, you should be at a different level than at the end. Now, maybe this is a daunting list, but think about it like this. Maybe you can take one mathematics course per semester if you are a PhD student in computer science. Maybe you can read one new mathematics book every semester if you're a PhD student in computer science. Of course, more can be always better, but I really think you might want to be practical with this. Just say, I want to do one thing per semester, pick one thing and try to work through it consistently. For example, one lecture that I really enjoyed taking as a graduate student, as one of the first lectures, was to take linear algebra from Gilbert Strang. He has a really nice book that I read, and he has great video lecture series about linear algebra. Very practical, very basic.
On with the example.
So here's a few seconds of Gilbert Strang.
2 equations, 2 unknowns. So let me take 2x.
Another really great linear algebra course, Introduction to Linear Dynamical Systems, by Professor Stephen Boyd, a really wonderful and gifted teacher. Here are a few seconds of Stephen Boyd.
So, welcome to EE 263, and I guess I should say for many of you, welcome to Stanford.
Also, I would like to note that it's important to study engineering mathematics, or engineering mathematics and pure mathematics. In computer science, we're often concerned with developing mathematical algorithms and then implementing them. So here's my view of engineering mathematics versus pure mathematics. In engineering mathematics, you might see some definition and then several examples, or maybe an algorithm and several examples. By contrast, in pure mathematics, you often have this definition, theorem, proof type of loop in the books and in the lectures. Engineering mathematics has many practical examples. You might see in engineering mathematics actual numbers. While pure mathematics, you only have few misleading examples or oversimplified examples to guide your learning. Engineering mathematics has finite dimensions. For example, in linear algebra, you might come across a 3 times 3 matrix. Pure mathematics is very interested in infinite dimensions and maximum abstraction, maximum generality. In engineering mathematics, applications is considered a virtue. Whereas in pure mathematics, applications are pure evil. One of the meanest things you can do to a professor in pure mathematics is if you find an application for what he's working on. Engineering mathematics has a lot of calculations. You might see, again, in linear algebra, there's a matrix. How do we calculate the determinant? How can we compute the singular values? In pure mathematics, we would try to prove theorems about the determinant, or we would prove theorems about the eigenvectors and eigenvalues. There's also the idea of applied mathematics. I do not like this term that much because, again, it is heavily overloaded. Some people say that applied mathematics is someone that simply works on partial differential equations or optimization. Even though the tools that are used can be almost the same as pure mathematics. In some cases, people use applied mathematics to refer to engineering mathematics, something that is quite practical. Unfortunately, applied mathematics is also the home of many failed mathematicians. They work on topics that are irrelevant for engineering, but are loosely inspired by engineering problems, but that are neither elegant nor complex nor abstract enough to find a home in pure mathematics. So I like the term engineering mathematics to emphasize that applications and impact in applications is an absolute requirement. Ultimately, in the past, there has been a great symbiosis between engineering mathematics and pure mathematics. Eventually, many great insights from pure mathematics have found their way into engineering mathematics. Also, pure mathematics has some of the brightest, most ingenious and talented people and researchers in all areas of research. Also, some people working on pure mathematics are really brilliant and they could solve engineering mathematics problems with ease, and they can often make significant contributions to engineering mathematics. While this is rarely the case the other way around. Someone working in engineering mathematics might find it extremely difficult to contribute to pure mathematics. If you can afford it, my advice would be to study both. Pure mathematics, at least at the undergraduate level, and engineering mathematics at the undergrad and the graduate level. Let's talk about subject skills. I use that to refer to knowledge of the latest techniques in your research area. In my research area, visual computing, maybe graphics, visualization, and vision. So again, these are specifically, maybe more specifically to my area. So in computer vision, I would try to look at CVPR, ECCV, and ICCV. In graphics, I would look at SIGGRAPH and SIGGRAPH Asia. And for deep learning, I would look at ICLR. Then I also look at, this should be NeurIPS, there's an R missing, NeurIPS and ICML for machine learning, but mainly as far as these are deep learning papers. Also, just knowledge of important algorithms in an area or textbook knowledge. English skills, I would include here written English, spoken English, technical writing specific to your discipline, conference, journal, just so you know how to write a paper that is going to get accepted. You need the ability to express ideas clearly, and you need the ability to structure and write a paper. What I see often is that actually some people can be pretty good at writing, but they can be not so good at speaking. And others can be really good at speaking, but they actually struggle writing papers. Since many engineers struggle with the ability to express the ideas clearly, there's often the confusion about English skills being the main reason, or lack of English skills being the main reason that a paper is rejected by reviewers. Often it is the case that someone might struggle with English, but they really fail to express their ideas clearly. So you could also think of this point more as English and general language presentation skills. Also, depending on what you want to do, don't underestimate the importance for spoken English for getting a good job and doing well in a job interview if you apply to an English-speaking company. While most students in the beginning of their studies struggle a lot with expressing their ideas clearly and structuring and writing a paper, this is something where I often observe that students really get a lot better during their studies, especially during PhD, where there's more time to improve the writing skills. Last but not least, creativity is an important skill. The ability to come up with new interesting solutions and the ability to come up with new interesting research problems. creativity is a key skill for a great researcher. Strangely, creativity seems to be unrelated to technical and mathematical skills. I encountered many brilliant people in my career, and some of these people are technically and mathematically absolute brilliant. They have no problem understanding the most complex material with ease. They can read large amount of information and absorb it in breathtakingly quick time. However, when asked to create a new idea, they draw a complete blank. They cannot create new ideas, or it is very, very difficult for them. Some people have constantly new ideas what to work on. This is really helpful if you want to be a researcher or an independent researcher. Also, it is easier to come up with new ideas once you have more experience with a particular topic. So, let's say if you already worked on one topic guided by your advisor and you read 20, 30, 40, 50 papers in a particular area, it might become easier to create new interesting solutions or new interesting research problems. Now, discussing all these skills again, obviously very few people are great at everything. Most people, even really successful researchers, they might have gaps in one or more of these areas. Maybe you're not so great in mathematics. Then, hopefully, you're really good with system skills and getting things to work. You can learn a bit more mathematics, but don't pick a topic that is very, very heavy in theory. Maybe you're not so great in creativity. Maybe your advisor can help you out a bit more in setting the vision for your research and proposing at least a few general and interesting research directions that you could explore more. Maybe your undergrad is in mathematics and you don't have a vast amount of programming experience. You can still do great research in computer science by picking something that is a nice combination between programming and mathematics. Subject knowledge is always something that can and typically is learned during a PhD or during a master thesis. It's not something that people typically have at the beginning. English, at the same time, I've seen people, they started out a PhD with poor English skills and then they improved. Sometimes they improve a bit and sometimes they improve a lot. But to me, the one skill that cannot really be compensated and the one skill that is absolutely a requirement is the love of research. You really have to be motivated and you really have to work consistently, continuously, and focused on a research problem. To me, really, the love of research and motivation is absolutely essential. In addition, it is worth noting that many research projects are team projects. Still, there's one PhD student that should be mainly in charge of his own project, but it is not uncommon that there are other people maybe helping out, correcting and refining the mathematics, maybe even helping out programming, help with writing the paper, and help with discussing the vision and the direction of the research project. Let's discuss a few differences between research fields. Not all research fields are equally difficult. Also, not all research areas are equally useful. Some areas require a lot of skills, and other areas you can start directly after undergraduate to be a productive researcher that publishes at the highest level. Some areas have very competitive top conferences. Other areas have only averagely competitive top conferences. Don't try to compare yourself to people in other areas. You might find that in some areas, people are publishing 20 papers. Maybe in your areas, 3 papers that are good is already a very respectable output for a PhD. If you ask a professor, they will typically tell you that their particular research field is the most difficult and has the most difficult competitive top conferences. Of course, not all professors can be right. Since I started publishing in computer graphics, obviously ACM SIGGRAPH is the most competitive conference. My colleagues in systems tell me that systems has the most difficult conferences. And my colleagues in machine learning claim that machine learning is the absolute top and most competitive field. This can be debated forever. What I think is maybe a bit more meaningful is if you try to find out for your area what is the top conference, maybe the top journal, and try to figure out how many papers can other students at other universities publish at the top when they finish a PhD, and how many papers do people have when they obtain a faculty position. It also helps to maybe be a bit more specific in the questions. How theoretical is a research area? If you're reading papers, do you mainly find theorems with long proofs of these theorems, maybe people proving bounds or other type of mainly mathematical proofs? Or is the emphasis on creating working systems or algorithm development? Some areas might appreciate you proposing a new algorithm that can solve a particular problem. Other areas might mainly be excited if you prove certain properties of an algorithm. How much mathematics do you need? Can you get by with very little or almost no mathematics? Do you need slightly more advanced undergraduate mathematics, maybe graduate mathematics? Or do you need at least an undergraduate in mathematics or statistics? How application-oriented is the research? Do you try to solve actual practical problems? Or is the research area concerned with loosely inspired problems that once resembled an application problem, but are really developed in such a way that there's no strong coupling between application and the research? Also, how saturated is the research area? It can be very difficult to publish in a saturated research area. It is important to choose your research area wisely. Unfortunately, this is mainly useless advice because you will select the research area, unfortunately, more often than not, without really knowing what the research is about that well. Many times, people only find out after 1 to 2 years how the research process really works and what a particular area is really about. I would also like to remark that taking undergraduate courses can be very different than doing research. In my example, when I worked a lot in computer graphics, many people thought that their love for computer games, or maybe the interest in implementing computer games, would be a good basis for doing a PhD in computer graphics. But then a PhD in computer graphics might have been about physical simulation of light transport and Monte Carlo integration. Many people apply machine learning techniques to some data, maybe medical data, during the undergrad projects. And then think this would be a good idea to do a PhD in machine learning since they enjoyed applying SVMs. However, applying certain machine learning tools can be completely different. A lot of machine learning, and I would say traditional machine learning, is almost entirely mathematical. You would state some theorems and then provide proofs for them. At the top level, there would be no space for applying certain tools, such as SVMs, to new and exciting types of data. Or maybe you find out you really enjoy solving 2D integrals in your calculus class. This is absolute no indication what a PhD in pure mathematics will be like. You should consider the differences between the skills used in the research area and also the skills that help you to get a good job. In many research areas, they are completely aligned, and in other research areas, this can be quite different. There can be some sort of a gap. We'd call this the football player problem. There are highly prestigious and highly coveted jobs available in the NFL. That means American football. However, there might be 10,000 or 100,000 people that are dreaming about obtaining one such position where only one position is available. In certain areas, I would say mainly the theoretical areas, only top people can get jobs. There's no job market for good or very good theoreticians. There's no job market for good or very good mathematicians. If you want to make proving theorems your life, you better be extremely good at it. This doesn't say that maybe after being a good theorem prover, you cannot get a really nice job as an engineer. However, it is unlikely you can get an academic position proving theorems for the next 40 years. In a good research area, good and top people can get jobs, meaning faculty jobs or research scientist jobs in industry. Maybe good research area is the wrong way to phrase it, but let's say in a good case, there are a lot of research jobs available, a lot of really exciting jobs available. As a side note, if you want to do a PhD or an MS with thesis, you typically need an advisor that agrees to work with you. Something that does not work well is try to ask a professor to start on research without having taken any relevant coursework or having done any relevant projects in an area. Also, many people are not excited to work with you if you get a B in related courses. Typically, people would like to see a solid A effort in a particular area in order to do research with you. You know that if you're driving a car, that everybody who drives faster than you is crazy and reckless, endangering the public, and everybody who drives slower than you is an incompetent driver. While in computer science, we cannot compete with the elegance and technical complexity of pure mathematics and theoretical physics, we will simply claim that computer science is a lot more important. In computer science, we only have biologists and chemists to make fun of for their lack of technical sophistication. I hope no biologists or chemists will listen to this talk. If this is the case, I apologize. However, I somehow really believe that computer science is really important. If you look at some of the top companies in the world by valuation, Apple, Facebook, Amazon, Google, these are computer science companies. There's at the moment no shortage of companies looking for computer scientists, looking for people with a computer science background. I think it's a great time to study computer science. It's a great time to be involved in computer science. When I studied computer science in a different era, there were multiple research areas: databases, networking, computer graphics, computer vision, AI. The world is different now. Computer science is a box that is filled with an inside box that is very big, which is AI. AI is completely dominant at the moment. In fact, it is so dominant that many other areas outside of computer science gave up whatever they did before and joined the quest to do AI. Electrical engineering now wants to do AI, biology wants to do AI, and believe it or not, even mathematicians, they want to do AI now. You want to work in computer graphics, heavily influenced by AI, computer vision, AI, natural language processing, AI, data mining, AI, databases, probably AI now, networking, not so sure, probably AI, but you will see this is a strong trend in computer science. But what is AI? AI itself is a box that is filled with 90% machine learning. Traditional AI, such as logic or planning, is a fringe topic. But machine learning by itself has been dominated by deep learning in the last 5 to 7 years. Traditional machine learning was about writing 30-page proofs of certain theorems that had loosely to do with machine learning. But it was, in fact, some form of mathematics. It was mainly about proving theorems. With the rise of deep learning, I would say that machine learning is a split community where some people still do theorem proving and some do deep learning. However, my belief is that deep learning is absolutely dominant. In general, I believe that deep learning nowadays is the most dominant force in computer science. Therefore, I am working on deep learning, as you might have guessed from this slide. But in research, nowadays, you will find three main types of researchers. Researchers that do work on machine learning or deep learning, researchers that pretend to do machine learning or deep learning, but they really work on whatever they worked before. They just try to sell it with a different spin. And researchers that consciously avoid having anything to do with machine learning or deep learning. The latter type usually has a prepared statement of why they don't work on machine learning and deep learning and how the area is going to be doomed and will collapse any moment. However, deep learning was supposed to collapse in 2015, 2016, 2017, 2018, 2019, and 2020. It's still here so far. But at the moment, deep learning is a really exciting field with still so many open questions and many exciting opportunities. But let's go back to this initial question of what skills are important for high-quality research. I strongly believe that system skills, meaning programming, getting things to work, combining code, and being very quick about it, is extremely important, and mathematics is very important. If you pick up one or both of these skills during your PhD or during your graduate experience, most likely you will be fine, even though you might have to change your topic after you leave. By contrast, the subject knowledge, while really important to do current state-of-the-art research, is a less lasting skill. It is something that has to be constantly refreshed. But then at the same time, if you have strong system skills and strong mathematics skills, you are able, in general, to switch your research area, often also very quickly. This is not an endorsement to switch research topic multiple times during a PhD. That is more a recipe for disaster. However, I think that a really valuable PhD is one that teaches a good mixture between programming skills and mathematics. These are two highly valued skills on the job market. As a tool, I really like this website, CS Rankings. What the website does is it has a list of research areas in computer science, and for each research area, it has a good selection of the most competitive conferences in that area. Artificial intelligence is AAAI and ICHCAI. Computer vision, you see CVPR, ECCV, ICCV. Machine learning, you see ICML, KDD, NeurIPS, NIPS, and you can also check maybe databases, Sigmod, VLDB. To me, this website is a good tool to find out what are the different research communities and what are top conferences. And then to find out more about the particular area, it really helps to read papers in these conferences listed here in the last 1 to 2 years. This gives you some good idea to judge a research field, at least at a superficial level. You can see what topics do people work on, how much mathematics is needed to write one of these papers, how much implementation do people seem to do for each of the papers, how big is the community? Are there 1,000 papers published per year or only 30? Are many of the papers consisting mainly of theorems and proofs, or are people involved in building systems? All right, I have a lot more slides, so I might decide later to record a second part of this. But for now, I'm gonna conclude the presentation and thank you for your attention.